Longer battery life is important for mobile phones and other mobile devices. A key part of determining a mobile device's runtime is validating the battery's capacity and energy ratings. If you determine a device's runtime based solely on a manufacturer's datasheet, without validating the battery's ratings, your results are likely to be inaccurate. The stated capacity is often based on ideal conditions and represents the maximum charge you might obtain from the battery. Actual capacity will usually end up being less when you verify it in your application. Battery capacity is the amount of charge in amp hours or milliamp hours that the battery is specified to hold. This is different from the battery's energy rating, which is measured or expressed in watt hours. You can determine the energy rating by taking the product of the battery's capacity times its stated nominal voltage. Because the battery's actual energy content can be more a factor in a mobile device's runtime than the battery's capacity, it is important to validate both of these values. Temperature and battery age also affect how much charge might be obtained from the battery, so you also need to consider these factors when you determine the runtime that can be expected for the mobile device. Very small differences in charging and discharging conditions can lead to large differences in the capacity and energy obtained from a rechargeable battery. That is why it's so important to precisely replicate and control all conditions in order to achieve good results. One key condition is the discharge rate, or C rate, usually stated as a constant current discharge at some ratio of the amp-hour capacity rating. A manufacturer may specify a discharge C rate of only 0.3, for example, because higher discharge rates will lead to lower capacity and energy delivered from the battery. For a 1 amp-hour battery, a C rate of 0.3 would be a 0.3 amp constant current discharge. Using this C rate would theoretically discharge the battery to its cutoff voltage in 3.33 hours. It is also worth noting that the measured energy rating can differ from that based on the stated nominal voltage, as the actual battery rundown voltage profile may lead to a slightly different result. Precisely controlling test conditions while accurately logging both the battery's current and voltage assures accurate and consistent results when determining the battery's capacity and energy ratings. Agilent Technologies has superior tools designed specifically for characterizing batteries. The N6781A source measure unit is tuned for battery testing. When combined with an Agilent N6705B mainframe and 14585A software, it is a superior solution for measuring and analyzing battery capacity and energy. We use the setup depicted here to discharge a rechargeable mobile phone lithium-ion battery at a fixed C rate. The full 2-quadrant capability on the Agilent N6781A source measure unit makes it well suited for use as a precision high-performance electronic load, as well as a precision DC source. The Agilent 14585A software was used to quickly set up and display long-term data logging results for validating the capacity and energy ratings with a constant current discharge of 0.3 amp and a 3-volt cutoff voltage. The results are shown here. Placing measurement markers at the start and cutoff voltage points on the data log revealed that the battery delivered 879 milliamp hour and 3.32 watt hour. Both of these values were notably lower than the 1 amp hour and 3.6 watt hour ratings obtained from the battery's datasheet. The next steps are to identify what factors caused the difference, and then assess if additional capacity can be extracted from the battery or not. As you have seen, it is best not to assume the battery's rated capacity and energy are what you will actually get, making it important to validate them as part of determining runtime for your product. For more information, visit the Agilent website at www.agilent.com/find/N6781.